too upset. So we're going to work on the worksheet. Let's start with question 3. Okay, so I want to give you all, this one's not too bad. So I think I'll give everyone about 5 minutes. And of course, if you want to, ask questions in the chat or come on mic and ask questions, and I'll be happy to answer them. But let's spend about 5 minutes and try and determine, is this GCD relationship, is this symmetric, transitive, reflexive, is it an equivalence relation? And it should go pretty quickly, okay? I couldn't find your notes on Quarkus. Are you going to upload your annotated notes from Monday? Maybe I forgot to upload them. Let me check just real quick here. Lecture recordings. Oh yeah, you know what? Maybe I didn't post them. I'll post them after lecture. Okay, Tima? Yeah, let me post them after lecture. And unfortunately, you're all going to have to constantly remind me, because the stupid thing about the way that this works, what I'm going to do is I'm just going to share the OneNote notebook with you. But because it's actually registered with the university, that link expires every 30 days. And so because it expires every 30 days, I have to refresh it every 30 days. So there might be a couple times during the year or during the term where you guys have to be like, oh, hey, that link expired. Can you refresh it, please? And then I'll do that, right? But yeah, okay, so everyone, right now we're going to work on worksheet problem number 3. I'm going to give you 5 minutes. So at 3:20, we'll take it up and I will show you my solution to it. Okay, so give that a shot. And like I said, don't hesitate to ask any questions in the chat or wherever you want. Like I said, if you want to come on mic, you can totally do that. And then I'll take it up. Okay, everyone. So now I've written an abridged version of this on my Surface on my OneNote. I'm asking, is this an equivalence relation? And immediately we're going to find that it isn't, right? It fails immediately. It fails reflexive. Yeah, definitely. It's not an equivalence relation, but nonetheless, we're going to go through all of them, right? We're going to go through reflexive, transitive, symmetric, and just see what it is that we get. So let's start with reflexive, which again is supposed to be the easiest one. And you would imagine, when you give questions like this, are usually not the thing that fails, but well, you guys actually, well, no, I've given it away, right? Reflexivity is going to fail. So reflexive. So we want to show that every element in Z0, 0, so every non-zero integer is related to itself. That's not going to be true though. So we want to show that A is related to A for all A in Z0, 0, right? But this is only true. The GCD of A with itself is what? Be careful though, it's not very close. It's not A, it's, we're going to see who remembers the technical definition of GCD. There's a little twist. No, it's not 1. So GCD would say that there's no divisors other than 1. Justin, exactly. It's the absolute value of A, right? And you might say like, yeah, I knew what the answer was. Why are you being technical like that? But we have to be careful, right? The definition of the greatest common divisor is the largest positive number which divides both of them. So we need to make sure that we take the absolute value here. It's not a big deal, but we have to be a little bit careful when we do it. So it's going to be the absolute value of A. And so if A is not equal to 1, or if the absolute value of A does not equal 1, then they're not related to each other. Then A is not related to A. So immediately we fail reflexivity, right? So thus, the relation is not reflexive. All right, bad start. Now, if the question really was just, is this an equivalence relation, we would stop. But the question actually asks us to prove all of them. So let's try symmetry. So you tell me, is it symmetric when you did it? Did you manage to get symmetry? So symmetric, yes, or symmetric, no. Okay, yeah, so we've got, all right, okay, so we've got some yeses. And if we wanted to summarize it like without doing any math, like what would your argument be? Like, why is this obviously symmetric, quote unquote, obviously? Yeah, it's that, exactly, Marcelo, it's that the GCD is symmetric, right? So the relationship is defined entirely in terms of the greatest common divisor. And certainly the greatest common divisor doesn't care whether you do A, B, or B, A, right? So we can immediately see this is going to be symmetric. So enough so that I would just say if you wrote that sentence down, it is true. But we'll go through the gist of it, right? Just so that everyone is on the same page. So suppose that A is similar to B, or A is related to B, right? So that GCD AB is equal to 1. Right? Then the GCD of BA, GCD of BA is the GCD of AB is equal to 1. So B is similar to A. And again, I would honestly, in my opinion, if you don't want to write all that crap down, you don't have to. You could just say the GCD is symmetric, so therefore the relationship is 2. Maybe that's the same number of words, but whatever. Okay, now you all tell me, is this relationship transitive? This is probably the hardest one. Any guesses? It's 50-50, right? It either is transitive or it's not. So, okay, we've got no, we've got no, 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 uncertain no's. Okay, so, okay, overwhelming, even if it's not with confidence, democratically, we seem to have come to the conclusion the answer is no, and absolutely you're correct, the answer is no. And one thing that we could do, let A equals C, GCD AB equals 1, and GCD BC equals 1. Right, but that doesn't guarantee that the GCD of A and C is 1. And rather than, so what I want to recommend, though, that when you do here, when you're trying to think of a counterexample, this is not the case where I think you actually want to push through the GCD. What you want to think is this relationship says that A is related to B if A and B are co-prime, right? So can we think of two numbers which are like two sets of numbers which are co-prime to each other, but A is co-prime to B, B is co-prime to C, but A is not co-prime to thing. Right, exactly, Paula. So 5 is related to 7, so no, since 5 is co-prime to 7, right? So they are related, and 7 is co-prime to 10, but 5 and 10 are not co-prime because their GCD is actually 5. But 5 is not related to 10, since the GCD of 5 and 10 is equal to 5, right? So that's the sort of one that I think is probably, you could actually get distracted if you're trying to think about it in terms of the mathematics. Sometimes you need to black box it or move up a little bit and think about the question a bit more abstractly, or not abstractly, even like, what is this trying to say, right? What is the definition of this relationship actually trying to capture? And if you think of it in terms of coprimality, I think it's a little bit easier to see the counterexample, right? That it's not going to hold in that case. Okay, so perfect. So that's question 3. Question 4 is pretty quick. So let's do question 4. I'm going to give you like 3 minutes to do question 4 because I think it's pretty quick. You can use a counterexample to show that it's not transitive. Yes. And in fact, Wei-Zhen, we could have done that for reflexive as well. I maybe, for reflexive, I could have just said 2 is not similar to 2. Right? Because their GCD is equal to 2. So I could have used the counterexample, but I thought it was worthwhile to kind of show that it actually fails for almost everything. So that's why I did it more generally. But yeah, if you want to show that something's not true, you just have to provide a counterexample. So I could have done that for reflexive as well. Okay. Okay, so for question 4, we've got S a finite non-empty subset of natural numbers, and we're going to define a map from the collection of finite non-empty subsets into the sums. The question is this thing well defined? I'm going to give you like 3 minutes to think about it. Because this one, right, there's not a lot to do. It either is or it isn't. So if it's not, come up with a counterexample, and if it is, justify why it is. Okay. All right, so for question 4, I mean, how long does this thing need to be? First of all, what do you think is it well defined? Okay, so I've got a yes. Sure. Yeah, that's kind of like the I'm not certain, or kind of passively yes. Yeah, it is well defined. And how long this solution should be really depends on how kind of intimate you want to get with it. Honestly, my answer to this when I worked it out is like obviously, period. But maybe that's unsatisfying. I mean, the sum of a finite number of things is always well defined, right? The sum of a finite collection is always well defined. Now, if you really, really want to stretch it out and somehow be rigorous about this, what you could do is say, suppose A is equal to B, right? So you want to show that f of A is equal to f of B. To show that f of A is equal to f of B, but like clearly they are, since f of A is the sum over all the elements in A. And since all the two sets are equal precisely when they have the exact same elements, right? So those are just the sum over all the elements of B. And so, I guess you could do this if you want. And then if you really weren't certain, like, can I write that these two sums are equal? You could be like, okay, well, they're both finite, so enumerate them, right? A as A1, A2, dot, 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 AN, right? B as B1, dot, 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 through BN. Assume that A1 is equal to B1 because you can do that without loss of generality by renaming them, yada, yada, yada. Who cares, right? Like, clearly, I think that this is okay, and we're not too worried about it. Now, though, bonus question, is it true if A is not finite? Right? So maybe like bonus. So what if we remove the finite restriction? So that's number one. Number two, what if I want to? That question is maybe easily answerable. I'm gonna let you think about it. Okay, so question 5. So we want to prove. I love this question because this question is like, I think it requires a little bit. It doesn't require a trick per se, but it kind of requires that you think about it, right? So we want to show that for every integer n greater than or equal to 2, there is a list of n consecutive integers. It says integers, but we can take natural numbers. There's a list of n consecutive natural numbers, none of which are prime, i.e. they're all composite, right? So let me set this up for, or actually, no, I'm going to let you try it on your own first, and then maybe I'll give you the hint. But my recommendation here is, what does it mean to be consecutive? I think this is actually the critical question. Okay, what am I trying to do? So show for all n greater than or equal to 2, there are n consecutive composite numbers. Okay, can anyone think about like how we would phrase this mathematically to make the problem maybe a little bit easier? What does n consecutive numbers mean? Their difference is less than n. Okay, sure. So if I wanted to enumerate them, let's say if I wanted to write down, let's choose a number. Okay, let's choose 4 consecutive. I'm going to choose 4 consecutive numbers. Okay, what does, if I wanted to write down abstractly, oh yeah, okay, so in order, so they have to be in order. And I also need to specify where they start, right? So I need to specify their starting point. So let's say they start at S. So let's say I want S plus 1, S plus 2, S plus 3, and S plus 4 to all be composite. Does that make sense? Right? Those are 4 consecutive numbers, right? And so really our trick is to figure out what should capital S be? What should our starting point be such that S plus 1, S plus 2, S plus 3, and S plus 4 are all guaranteed to be composite numbers. Okay, and I think that with that hint, that will make it a little bit easier. And then obviously, and if you want to actually do it in the case where n is equal to 4 to begin with, and then extend it to the general case. And once you figure out how to do it for 4, you can probably figure out how to do it for n. Like hopefully you'll see what the pattern should be. Okay, so let's spend like 4 minutes doing that, and we'll take it up at 40. Okay, so this one a little bit trickier, right? Again, let's just worry about when n is equal to 4. And I don't even want to solve it right away. I want to see if we can come up with this together as a class. What is, if I look at the number s plus 1, screw s plus 1, s plus 2. If I look at the number s plus 2, how can I really easily guarantee that it's composite? What number should I say divides s plus 2? An even number, sure. Yeah, 2 is a great number too, right? Because I know that 2 is going to divide the plus 2 part, right? So if I also demand that it divides the s part, then I'm in money. So let's demand that 2 divides s plus 2. In particular, because what I'm trying to think here is like, listen, the 2 certainly divides that 2, right? And so same sort of thing. If I, what should, I gave that away. Sorry, I'm being dumb. So I'm going to also divide, I wanted you guys to get this, but I gave it away because I'm not thinking. I'm also going to demand that 3 divides s plus 3. Does that make sense? Because I can guarantee that the 3 divides that 3. All right, does that make sense? And so what I'm trying to do here, everyone, is I'm trying to figure out what should capital S be, right? Because if I can figure out what capital S should be, then I'm in the money. So same sort of thing, I'm going to demand that 4 divides s plus 4. And all of these conditions implies that 2 has to divide s, 3 has to divide s, and 4 has to divide s. Okay, sure. So eventually, if we get like, well, so Sunxiao, what we're going to do is if 7 is a bad number, we're not going to let s be 7. We get to choose what s is going to be, right? So what I'm trying to say is let's figure out a condition which guarantees that 2 divides s, 3 divides s, 4 divides s, and so on. Exactly, n factorial will give it to us, or in this case, 4 factorial, right? So in this case, setting s to be 4 factorial will work. And of course, we didn't actually, need to do 4 factorial, right? Like 12 works, for example, because we know that 2 also divides 4. But let's not complicate our lives. We don't care that the number is stupid big. We just care that the number exists. So the idea here is that when I want to guarantee that there are n consecutive when I want to guarantee that there are n consecutive integers that are composite, what I just need to make sure is that that number that I'm starting at, that number s, is divisible by 1, 2, 3, 4, all the way up to n. And the easiest way to do that is going to be to set it to be n factorial, right? So the claim is that the set n factorial plus k, where k goes from 1 to n, are all composite. Right, and the proof of that, so let k, or fix some n factorial plus k, where k is in 1 through n. Note that k divides n factorial plus k, right? Because in particular, k is less than n. Hold on, I'll read that one in a second, Hong Wei. Let me just finish this. So n factorial plus k is a composite. right? And the idea there is now we're done. So what about n equals 2? That way s equals 2, but 2 plus 1 plus 3 is not composite. Right, okay. That is an interesting point. So we've got n factorial plus 1 and n factorial plus 2. Oh, maybe we just want to, how do we prove s plus 1 is not prime though? Okay, that's true. Actually, let me think about this. How do we prove that s plus 1 is not prime? Because it could be, right? Why is s plus 1 not prime? Well, okay, listen, let me put it this way. Then what I've done, if we want to do it for n, why not use n plus 1? Right? Because for sure, here, these are n minus 1 composite numbers. So here, let me cheat a little bit. There are for sure n minus 1 composite numbers. Should it start from 0? I think we still run into that issue though, where n factorial plus 1 could still be prime, right? Right, we still have that issue. So if we start at n factorial plus 2 and go to n factorial plus n, then we're okay. In fact, maybe we need to start at plus 2 and go to n plus 1. No, because we don't know that n plus 1 divides n factorial. So either way, we can cheat and we can say, listen, this for sure defines n minus 1 consecutive numbers. Do you agree? Like if we start at 2 instead, let me just cheat a little bit and start at 2. Do you all agree that this defines n minus 1 consecutive numbers? Okay, and then now that proves it for everything, right? Because you say to define 10, and so I let n be 11. And you say, give me 300 consecutive numbers, and I use n is equal to 301. Right, does that make sense? So we can kind of like cheat around it. You're right. That's actually a really good point, Hongwei, like that S and Paula as well, that n factorial plus 1 could have been prime. So very good point. And we'll sweep that under the rug by saying we can just cheat and use n plus 1 instead of n factorial. Okay. Any questions?
Wait, sorry, what was the cheat again?
The cheat is if using n factorial, so throw out the plus 1, right? So use n factorial and start at plus 2 and go to plus n. That gives us n minus 1 consecutive integers. But if you can prove that there are always n minus 1 consecutive integers, you've basically proven it for any n. Okay, I don't think we're going to have time to do both 1 or 2. So I'm going to let you all choose what it is you want to do. And I will say it with the following caveat. I think you'll all get 1 eventually, right? It's just a matter of playing with inequalities, but you have to kind of like, there are at any given time multiple inequalities you could do. So there are multiple paths you could take, and you have to always choose the right path. But I think you'll all eventually get question 1. I suspect question 2 will actually fundamentally stump you, and that many of you will not be able to get question 2. So given that, put into the chat what question you think we should do next. Well, luckily 2 factorial is 2, Marcelo, right? So I assume, again, that was just an exclamation, not a factorial. Okay. All right, so we're going to do question 2. And again, I'll give you a couple of minutes to struggle on it. And hey, maybe you'll surprise me and maybe one of you will come up with an answer, which will be phenomenal. I'll be so happy. But otherwise, let's spend a couple of minutes trying to work on question 2 and let's see if we can make any progress. Okay, so we only have so much time and I need to I want to make sure that I actually take this up. Does anyone think they got it? Like I think it's obviously an induction question, and I've already written out the base case just so that I don't have to, I think we all could have done the base case. Does anyone think that they managed to figure out the trick? I guess it's not a terrible trick, but I think it's a little dirty. Yeah, I think this is Oh, interesting, Kenneth. Like, how did you brute force it? Because that's a, because I mean, you do kind of have to brute force it, but there's a dirty trick to make it work. Okay, let me just write down the induction hypothesis. So suppose 2 to the 3, let's use k, minus 1 plus 5 times 3 to the k is divisible by 11. Right? And here's kind of how you do. So yeah, I mean, so, okay, so here's what we're going to do. I am going to, yeah, so I'm going to plug in the next integer. Let's see. So I actually did 2k plus 2. I guess actually, yeah, you could have done k plus 2. Is it going to actually be easier if you use k plus 2? Let me try it your way. Okay, I'm going to try the proof kind of originally, and we're going to see if it works. When I did it originally, I used 2k plus 2 instead of k plus 2. But let's see if that works. Actually, I'm running out of time. Maybe I should just do 2k plus 2. So no, whatever. Let's try it. So subbing in k plus 2, we get, so we're going to get 2 times 3k plus 2 minus 1 plus 5 times 3k plus 2. And that's going to be 2 times 3k plus 5, right? Plus 5 times 9. Or maybe let me just write it like this. Times 3k 3 squared. And so that's going to give me 64 times 2 to the 3k minus 1, right? Plus 9 times 5 times 3 to the k. Right? Does that make sense? And the reason you might say, like, why, where is the 64 and the 9? So the reason why I did this, right, is because I'm trying to reduce this to the things that I saw before, right? I know that my induction hypothesis tells me something about 2 to the 3k minus 1, and it tells me something about 3 to the k. So I'm trying to make sure that those show up, right? And I think, Kenneth, that's what you're saying, right? Is like you manipulate the exponents to make sure those things show up. Okay. Now, what I want you to do is look at these numbers right here, okay? Look at the 64 and look at the 9. So where is take the 9 from the 64? I don't know how you're going to do that because they don't, like, you can't factor it out. Or what? Oh, you're going to make it 55. Oh, I see what you're going to do. Sure. So I actually, yeah, I guess you could do that. Yeah, sure. Kayla, yeah, let's do it that way if you want. So that's not actually how I would do it, but that should work. So let's give that a shot. So we're going to write this as then 55 times 2 to the 3k minus 1, which is certainly divisible by 11. And then we're going to have 9 times 2 to the 3k minus 1 plus 5 times 3 to the k. Sure, you can do that. And then 11 definitely divides the left thing, right? Because it divides 55. So divisible by 11. And then this is divisible by 11 by the induction hypothesis. So the whole thing is. So we've proven, I'm just going to say, so we've proven the result. Nice, very nice. So what I actually would have done, I think this one's nice too. So I actually would have added and subtracted 2 from each of these, from the 64 and the 9, right? To make it 66 and 11, which basically gives you the same thing. It doesn't make a big difference. There's a sense in which I think your guys' one is cleaner, where you took the 64 from the 9. Yeah, I think that one's actually pretty clean. I like that one a lot too. But my thing would have been to add 2 to each, like add and subtract 2. Okay, so does that make sense, everyone? You see how that one's a little bit trickier though, right? Like you have to see this clever little minus thing that you have to do in order to make it work out. But that's going to take us to 4 o'clock now. So question 1 is, right, prove the inequalities separately. I don't think you want to try and do them at the same time. Prove that the root n is less than the sum, and then the sum is less than 2 root n. And like I said, at any given point, there's a couple of different inequalities that you could use to try and further it and simplify it. I think it's easy to get stuck if you kind of do what you've always done. I think the inequalities aren't necessarily the obvious ones, but if you play around with it enough, you will be able to just grind it out and get what you need to be true. In both cases, you basically have this like cancellation where you're going to have like n divided by root n, or sorry, n divided by root n, and that'll cancel out to give you the root n that you need. So those are the sorts of things that you're looking to do. Okay, so are there any questions about that? Play with question 1, see if you can get it. I suspect Ali probably started with question 1. So as well, if you don't have it if you can't find it, you can probably check out his recording, and I'm willing to bet he covered it. Okay. Otherwise, though, I think that'll finish it for us. Next week, so in terms of the readings and everything, we're actually going to start talking about groups. And so you'll see that groups are a relatively simple thing. They are a set with just 3 axioms, right? Associativity, the existence of an identity, and the existence of an inverse. And then, but from that, it turns out that we can create like this remarkably rich structure in theory. So give that a read, see what you can do. I think that this is a great time for you as well to start hypothesizing your own results and seeing if you can prove them, or trying to create your own examples of groups without having seen them in the notes. This is an excellent opportunity to do it because there's a real sense in which we're starting from scratch, right? And this is algebra from scratch. So many of the examples will be relatively simple, relatively straightforward. There's lots of low-hanging fruit in terms of results. So if you can hypothesize and prove your own theorems before we even get to them, then that's phenomenal, right? And so this is a good time to try and do those sorts of things as an exercise. But other than that, I think that's going to finish us off for today. So I'm going to kill the recording now.